In this section, we're looking at our business and economics applications. Here, we're trying to figure out where our maximum and minimum values occur. The maximum and minimum value for any function, whether business or algebra, occurs where first derivative is equal to 0 or where our first derivative is undefined. So we have to keep in mind these two conditions. Where our first derivative is equal to 0 or where it's undefined is known as our critical value. This critical value is just our x-coordinate. To find the actual maximum or minimum value, we need to substitute that critical value c into our original function and evaluate it. So our maximum or minimum value will be f of c. Or our maximum or minimum value could be defined as the point c, or x-coordinate, and the y-coordinate, f of c. We know that this is a maximum value at our critical value if to the left of c the first derivative is positive, which means our function is increasing. So here our function is increasing, and to the right of c our function is decreasing. So we can see at this point we do have a maximum value. Now the reverse is also true. If to the left of c it's decreasing and to the right of c it's increasing, then at the bottom we have a minimum value. What we will do now is look at a few examples that demonstrates this. So here we have an example with a revenue function where our revenue is given by 48x squared minus 0.02x to the third power. We're asked to find x, which is the number of units that will produce a maximum profit. Now, since it's a maximum profit question or optimization problem, we first need to find our first derivative and then find our critical numbers. Our first derivative, r prime, would be equal to 96x minus 0.06x to the second power. To find our critical value, we're going to set this equal to 0 and solve it. So we have 96x minus 0.06x squared is equal to 0. If we factor our x, we're left with 96 minus 0.06 x equal to 0. So x is equal to 0, or 96 minus 0.06 x equal to 0. Now here we have x is equal to 0. We know that 0 units will not produce the maximum revenue, right? So here we're going to set 96 minus 0.06x equal to 0 and solve this. So if we bring over the 0.06x and divide by both sides by 0.06, we get x is equal to 1600. So here this is our critical value, or the number of units that will produce our maximum profit. We can prove that this is true by also taking our second derivative. Our second derivative, r double prime, would be equal to 96 minus 0.12x. Now if we substitute 1600 for x into this, r double prime would be equal to a negative number. So this will be 0.12 times 1600 being taken away from 96. Now that will be negative. We know from our second derivative test that when our second derivative is a negative, that means our curve is concave up. Our curve is concave down, which produce a maximum value. So once again, the number of units that produces our maximum profit is when x is equal to 1600. Here we're trying to find the number of units x that produces a minimum average cost per unit. Now this average cost is defined as C over x. So our average cost definition is to divide C, our function here, by x. So our average cost would be 2x squared all over x plus 255x over x plus 5,000 over x. This simplifies to give us 2x plus 255 plus 5,000 times x to the negative 1 once we move the x up. And the reason why we move this x up is so that we can take our first derivative. Because remember, to find our minimum or maximum value, we need to find the first derivative and find our critical number. Our critical number occurs where the first derivative is equal to 0 or undefined. So let's go ahead and take our first derivative. First derivative of 2x is 2, of our constant is 0. First derivative of this becomes negative 5,000 x to the negative 2. Our critical number is where this is equal to 0 or undefined. We set it's equal to 0 and we solve it. If we move the 5,000 over, we get 5,000 over x squared is equal to 2, or x squared is equal to 5,000 over 2, or just 2,500, and then x would be equal to plus or minus 50, since 50 is the square root of 2,500. Now we know that it cannot be negative 50, since the number of units that to produce our average cost cannot be negative. So we know x equal to 50 is the number of units that will produce this minimum average cost. We can proceed to prove this by taking our second derivative. Our second derivative will give us, this goes to 0, this times this will becomes 10,000 x to the negative 3, or 10,000 over x to the third. Now if we substitute 50 for x to the third in for x, this becomes 10,000 over 50 cubed. Now it doesn't matter what 50 cubed is. This is a positive number divided by a positive number, so we know our second derivative evaluated at 50 is going to be positive. We know from our second derivative test that when we plug in our critical number into our second derivative and it's positive, we know our graph is concave up. So therefore it's a minimum value here. So at 50, because this is positive, it's at a minimum. So our answer would be 15 units will produce our minimum average cost. In this example, we're being asked to find the price that will maximize the profit, given that our demand function P is equal to 90 minus x, and our cost function is C is equal to 100 plus 30x. So we're trying to maximize profit, so we need to get an equation for profit. We know that profit is equal to our revenue minus our cost. So we already have a equation or a function for cost. We need to get an equation for revenue. Our revenue is equal to our demand function P times our number of units x. So here our profit function becomes R is P times x, so this becomes x times P, which is 90 minus x. So this is our revenue minus our cost, which would be 100 plus 30x. If we simplify this, we have 90x minus x squared minus 100 minus 30x, or negative x squared plus 60x, since we're minusing 30x, minus 100. So this is our equation for our profit. Since we're trying to maximize profit, we need to find the first derivative. So our first derivative of this would be equal to negative 2x plus 60. Now we know our critical value occurs where our first derivative is equal to 0 or where it's undefined. So if we set this equal to 0 and we solve it, we get x is equal to 30. Now, so this is a number here that will produce our maximum profit. We can prove once again that this is the number that actually produces the maximum profit by taking our second derivative and plugging this in. We take our second derivative, we find p double prime is equal to negative 2. Since p double prime is equal to negative 2, we know when our second derivative is negative, this is concave down, and if it's concave down, then it's a maximum. So here, this is a number of units that will produce our maximum profit. However, we were not asked to find the number of units, we were actually asked to find the price that will maximize profit. So the price that will maximize profit is here, or from our dividend function. So P is going to be equal to 90 minus our X, which in this case is 30. So our price would be $60 per unit that will maximize our profit.